learning target with scientific notation. So what we did with the previous lesson is we translated. We went from standard form to scientific notation, and from scientific notation we translated to standard form. Today what we're going to do is identify proper scientific notation. If you noticed yesterday, we always had numbers that look like this. I don't know, 3.04 times 10 to the something, 4.8 times 10 to the something, 1.2 times 10 to the something. Notice there was always one digit to the left of the number, okay? One digit to the left of the decimal was always the case, and that's proper scientific notation. The definition of scientific notation is that leading number is between 1 and 9, and that's from our notes yesterday. We do have that. So sometimes we have to convert numbers around to turn it into proper form. So I want you to cloud off this little rule. Writing in scientific notation, sometimes it looks like it's in scientific notation, but it's really not. Look at this first example. 0.387 times 10 to the 9th. That looks like scientific notation. It is not scientific notation. It is not scientific notation because I don't have one digit to the left of the decimal. And proper scientific notation needs one digit to the left. So we have to convert it. So there's a couple ways you can do this. You can go a long way, which will never steer you wrong, or you can think logically about it. I'll show the long way first. So 0.387 times 10 to the 9th. That is not in proper scientific notation. I can turn it into proper form by actually doing it, because it's still about moving the decimal. So I can go ahead and move the decimal 9 spots. So 1, 2, 3, 6 placeholder zeros. So 387, then 6, 1, 2, 3, 4, 5, and 6. 387 million. And then from there, I can write it in proper form. This would be 3.87 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8. That's the long strategy. You can always do that. You can expand it out and then decongest it again. The logical strategy, you could say, okay, well, 0.387 is not in the right form. I know that it has to be 3.87. Now I'm going to think logically about the exponent. It tells me I need to go 9 spots to the right, but I already went 1 spot to get it in proper form. How many do I have left? Let me restate that. The exponent right now tells me I need to go 9 spots to the right. Well, to translate it to proper form, I went 1 of the spots. How many do I have left to go? 8. That's the logic form. Okay, I'll show you again. This one, 12.98 times 10 to the negative 5. Okay, this is not in proper form. I need 1 digit to the left of my decimal. How many digits are to the left of my decimal right now? 2. 2. So I need to change it. It has to be 1.298. Has to. Now, what changes is your exponent, and you need to figure out what am I going to do to it. Because it's not going to be the same. You could go the long way. So you could move the 5 spots to the left. 1, 2, 3 placeholder zeros would be 1, 2, 3, and then 1298. So that would be, if I'm right here, I would need to go 1, 2, 3, 4 to the 4 to the left. Or think logically. So that's the expanding, that's the longer way. The logical way is I know it has to be 1.98 times 10 And then I think, okay, well it tells me I need to go 5 to the left. Well, I went 1 to the left to get it into proper form, so I have 4 more to the left that I have to move. You cannot see that. So I have 4 more to the left that I have to move. A student observed a couple of years back when I had them for Academic Edge, they had a really cool strategy at being able to do this. And they figure out how to change their exponent based on if they're making their digits smaller or bigger. Notice, at first I made this bigger. Since I made this bigger to balance it out, I make my exponent smaller. Now follow me here. So 0.387 turned to 3.87. And it's kind of like a yin and yang thing. You need to balance it out. Since I made this bigger, I'm making my exponent smaller. Okay? Now look at this one. I went from 12.98 to 1.298. Did I get bigger or smaller? I got smaller, so let's balance that out. Since I turned my number smaller, I'm going to increase my exponent. -5 plus 1 is -4. Okay? Got it? Okay. So that's what you're going to have to do today. You're going to have to convert things into proper scientific notation. And then another application of that is comparing. So when you compare, you want to make sure they're all in proper form, and then you compare the exponents. That's all. I mean, comparing with scientific notation is decent. You just have to make sure it's in proper form. So this one is not in proper form. I need to turn it at 6.8 times 10 to the, now I have to think about that exponent. I got bigger by 1, 2, 3. I got bigger by 3. That means I need to turn this smaller by 3. 6 minus 3 would be 3. Okay, and you can also think if I need to move 6 spots to the right, well, to turn it to proper form, I already moved 3, so I just have 3 spots left to move. The next one, 312 times 10 to the -4, not in proper form. It's 3.12 times 10, then think about your exponent. I got smaller by 2, so I need to get bigger by 2 for my exponent. So I'm going to plus 2 to that exponent, and I get -2. Okay, and my next one turns to 5.8 times 10. Now I got to think about this. I got bigger by 1, right? I got bigger by 1 because I moved it to the right, which tells me I need to get smaller by 1 for my exponent, so that would turn to 7. And now you can just order by comparing the exponents. So my smallest number would be 3.12 times 10 to the -2. And then my exponent of 3, 6.8 times 10 cubed, followed by 5.8 times 10 to the 7th. Because the exponent tells you place values. And so if you have more place values, you're bigger, aren't you? If you have more place values, you're bigger. If you have more place values to the left, you are smaller. And that's your target.